Good morning, everyone, and welcome to this Metal Additive Manufacturing conference. I am Nayara Zubizarreta, and I am in charge of ADIMAT, which is the Spanish Association for Additive Manufacturing. And we group together nowadays 110 companies that are experts on this field. And we are working hard to push the implementation of these technologies in the Spanish industries. We are here today because ADIMAT is part of the Additool project consortium. This is a project that is coming to its end, and today we are celebrating the last event where we are going to present the most relevant results of this project. And we have been working in collaboration with the consortium that is going to be presented by Pierre Diaz, which is the coordinator of the project. He is from STIA. STIA is a French institute of research in France. And he is going to give you a first overview of the project, what has been the main work that we have been doing, and what are the main results. And then we are going to also talk about future trends on metal additive manufacturing, and for that we have invited some key speakers, some relevant international speakers. And we hope you enjoy the morning, and thank you very much for coming. And Pierre, the floor is yours.
Thank you, Naya. So, good morning, everyone, and welcome to this final conference of the Additool project. So, to briefly introduce myself, my name is Pierre Diaz. I'm an additive manufacturing engineer in the Adimadour platform in Bayonne, in south of France, which is a technological platform that is specialized in metal additive manufacturing with a large dimension, and which belongs to the engineering school of STIA, like said Nayara, in the southwest of France. So first of all, before starting, I want to thank you very much, and thank you all for coming in such large number. We are more than 100 people, so it's very great. And to celebrate the end of the Additool project and participate in the various presentations. Also, I would like to warmly thank the entire organizing team of AFM and ADIMAT, as well as the Arima Hotel, without whom this conference wouldn't take place today. It's an exemplary organization, so thank you very much, all the team. And as well as the project partners for all the work accomplished during these last 2 years of Additool. And also, I would like to thank our distinguished guests who have agreed to come and discuss around topics of metal additive manufacturing today. And namely, we have Eric Vizix from the Department of Technology, Evaluation and Benchmarking at AM Power, who will talk about the sustainability of metal additive manufacturing. We have also Thomas Lecrin, DoD Technology Development Manager at ADUP, who will present DoD technologies and opportunities for the tooling sector. Thank you. Also, Gonzalo Nuno Rodriguez, PhD and Master of Science at Cranfield University, who will discuss the latest development on WAM technologies. Dominique Fleisch-Acker, application engineer at Adaxis company, who will address the multi-axis programming and the capabilities in the additive manufacturing sectors. He replaced at short notice Henri Bernard, who had a personal impediment and to whom we send our best thoughts today. So thank you, Dominique, for being here. And finally, Vincent Perrin, business developer at Rescol, who will talk about cold spray technology and its industrial application. So thank you, our guest. So Additool is an Interreg SUDOE project which covers all the entire southern zone of France, Nouvelle-Aquitaine, Occitanie, all of Spain region, and all of the Portugal region. Additool, follows a previous project we have, namely Addispace, and which aim to promote MAM technology, so Metal Additive Manufacturing, which we call it MAM, in the aeronautic and aerospace sector. And during this finalization of Addispace, we have a lot of feedbacks and a lot of opportunities to open and to address the tooling industry. That's how Additool was born. And it is very interesting because tooling business opportunity is the largest original industry for all sectors of industry. It relies on aeronautic, aerospace, but also you can have railway, automotive, energy, production, industry, etc. Plasturgy also. And the machine tool concept covers a wide variety of applications, including fixture, jigs, gouge, molds, die, cutting tools, etc. And with metal additive manufacturing, including options, with this kind of technology, we can be, in some application, not all, but in some application, we could be cheaper and or more efficient. Just an information, a fifth of companies active in the aeronautics and all the sector, automotive, mechanical, engineering sector, are using additive manufacturing technologies for developing their own tools. Okay? So this is a great sector and a great opportunity for us to address tooling industry through Additool. We can have some advantages, even if also CNC machines are generally considered to offer better cost and efficiency. Okay, MAM technology can address and can be the best options when it brings real added value. This is very interesting because with additive manufacturing we can have parts with real added value that we cannot do with machining or conventional technology, for example. We can have freedom of tooling design and the ability to create more functional end products. We can have a possible lead time reduction, okay, delivery time reduced, possible cost reduction, and also to improve tool performance. So through Additool, in the SUDOE region, we have some objectives we have to respect and we have to promote additive manufacturing. The first one was a contribution to the competitiveness of the industry in the SUDOE area, so south of France, Spain, and Portugal. Also, we want to generate a fundamental and applied knowledge, in relation to MAM process dedicated to the tooling sector. We want to promote also company investments in R&D plus innovation, develop some links, synergy between companies, research centers, and also with higher education. Okay, it's a trio. Then we have to strengthen the research, technological development, and also the innovation for smart and sustainable growth. And then finally, we have to transfer it. That's why we have the conference today and the webinar before. I will explain you after. To transfer the knowledge, again, in this project to the industrial sector. Additool can rely on 9 partners. The first one is ST Adimadour as a leader of the project. We have also the cluster Adimat, with AFM cluster, Additive Manufacturing, in San Sebastian. The Association Nationale of the Industry, CEFAMOL, Industry of Mold. The Research Center Laboratory CEIT in San Sebastian also. We have the Engineering School of Tarbes in Tarbes, in the south of France, in Occitanie. The Aerospatial Technological Center of Fadacatec in Sevilla, in Spain. University of Leiria, IP Leiria. The Research Center and Technological Platform Lortec in Ordizia, in Spain. And then we have the engineering school, the university of the Basque Country, UPV. So this is the 9 main partners of the project, but we can rely also, we can open the partnership with 9 associated partners, okay, that are just around us. The Agencia IDEA, we have the Andalusia Aerospace, cluster Hélice, the school ETAP in Portugal, Gestamp, we have the French group of Lawak, Tier 1 supplier. We have the cluster, the French cluster of Mechanic Valley in the center of France. We have also MEP for the modern industry, the Somocap industry, injection and production of flexible part, and also Trenasa in Navarre. And Additool, this is the center of the project and the main program. It's around 4 main work packages. The first one is the circle, the basis of the project, is the market study. The market study with a deep analysis of the tooling market. Okay, so we have an inquiry. I will explain just after. An inquiry with a lot of answers to give us a study for the opportunity study for the development of MAM technologies. And then, thanks to this market study, we can find 4 or 5 pilots to develop and to promote additive manufacturing technology in the SUDOE area. With this deep analysis of the tooling market, it's a report. It is a total of 85 entities from the tooling sector in the SUDOE that we have given us the inquiry and the answer. The answer to the survey, and this deliverable is available on the Additool website. Okay, so www.additool.eu, and available for free in PDF format in French, Portuguese, Spanish, and English languages. Okay. Also, the second deliverable was the study of opportunities. What we have to, what are the strategic part we have to develop in particular, okay, through the large sector of tooling. Also, this deliverable is available for free and downloadable directly on the website and in 4 languages: French, Portuguese, Spanish, and English. The second work package is when we have the basis, we have the 5 pilots to develop. And this is the improvement of our skills in additive manufacturing. Through this pilot, we have to gain experiment. Okay, we have to master the technologies, to modify parameters, etc. And we have to gain experiment, then to transfer. So we have developed new materials, new powder for metal additive manufacturing, characterization of wire and powder, so as for raw material, but also with specimen and after part manufacturing. Okay, so we characterize after, before and after the part was created. And we manufacture 5 pilots that each pilot leader will present just after the presentation of IM Power during 10 or 12 minutes. Okay, so we'll have all the information of the pilot. And then this is important to note that these pilots are not only demonstrators. They are not only showroom parts that we put on a table and is die. This is real pilots that are tested in real condition in the production line of the companies we have. Okay. And also, when we have gained some experiment and when we have increasing our skills in additive manufacturing, we want to, first of all, train and then to transfer to the industry, to the university, etc. And we have organized in Additool some training modules for students, 7 webinars, and we have created a mobility of the researcher and PhD also all around the project partner of Additool. Okay. The training course for students, we have created with all the partnership, 1 unique module, okay, developed by all partners, focus on MAM and for the tooling industry, tooling sectors. It's a module that dures 2 weeks in continuous, and in a space in the last 2 years, we have trained more than 60 people in this sector. Okay, with a program could be interesting for students with a global introduction to the tooling sectors and MAM technology to have a common basis for everyone. Then we have speak about the material adapted to MAM and adapted to the tooling sectors. We address also the multi-process design rules, because it's different to manufacture with laser powder bed fusion than in DUD powder or in DUD wire laser or arc. So multi-process design rules. Then we abord the topological optimization adapted to MAM. All apart also for programming. This is the main task of additive manufacturing. This is the programming of trajectories in DUD. So with machines and also with robots. And that's something is very interesting, is that all the students have manipulated. We can rely on a machine park through Additool, with Lortec, with UPV, with Estia, with Fadakatec, etc. We have all the technologies available, and all the students can manipulate robots, machines, etc., do the programming of trajectory, etc. And then we finish this module by a visit of local ecosystem for the curiosity of the students. Could be interesting for them. Just briefly resume on it, about the module they attend, and in terms of objectives and result of the prestation, we have a big satisfaction of the student. So yeah, we see 1 mark in green. We have a student that have put the mark 3 everywhere, so we have to live with this. We cannot satisfy everyone, but the big majority are very happy with this. In terms of quality of the prestation and satisfaction with the teacher, we have also the same mark. Maybe with the time of the realization of the prestation, they want more practical, more days to practice robots, to practice machine, etc. But generally, 2 weeks seems be good. This is the main interesting things we can solve out. It's how do you rate your level before the training module? Okay, so their feeling before having participated in this training. And we see 60% with basic experience and 40% with no experience. Okay? So this is the basis for the training. And after the training, we have rated 1 level more for everyone. And the people in the first diagram with good experience have converted to expert. So we have to recruit him, maybe. If it's an expert. Great, but everyone have rated one level more, so it's very interesting. And this is our 100% recommend these training modules, and we don't pay for this. Okay, in Additool also, in terms of transfer, the technology, we want to do not conference, but webinars, okay, to transfer each competence, each experiment of each partners that are specialized in one domain. And we organized, so at this time, 5 webinars, but 2 are pending on February 2023. And they are available in replay directly on the Additool website, okay? So we have a transfer with technology FDM metal charge with a non-destructive examination of metal additive manufacturing part by Fadakatec, boosting digitalization in the mold and die sector by UPV, powder atomization and post-treatment by SEIT, and then the topological optimization by Lortec. Okay, so I invite you to see these webinars. And don't hesitate to give your feedback on it to improve ourselves. And then the last part of Additool was mobility. We want in Additool for France, Spain, and Portugal to be, how say, to share best practices. Okay. We want to improve our skills at the same time and at the same level. Okay, so we organize a lot of mobilities. So more than 13 mobility have been organized. So STA come to Lortec, Lortec come to CEIT, CATEC also for UPV, etc. And we exchange engineers, researchers. We share also equipment. So we bring cameras. We have access to tomography, for example, etc. So we can have access to all the experiment of the SUDOE region. That is very, very interesting. All these deliverables and the report can be available at the end of February. They are not online yet, but you can find at the end of February on the Additool website. I am at your disposal if you have any question on it. And I thank you for your attention. And that's all, Nayara. Thank you. So now we will present the 5 pilot of Additool. So there will be only 10 or 12 minute presentations or short presentation, okay, to give the talk to the round table after. Just to notice that every results will be available on website at the end of February. So I give the talk to Carlos from FADA CATEC, Carlos Riobos, and we'll talk about the Spanish pilot 1. Yeah, here to you. You're welcome.
Thank you. Can you hear me? Yeah? Okay, so it's a great pleasure to have you all here. Let me introduce the first pilot, as Pierre said. Is in this use case, there are 2 machining companies involved as end user that are Meupe and Inespasa. Okay, both of them are located in Seville, like CATEC. In fact, Meupe is one of the associate partner in Additool project. Okay. Okay. First, a little bit of background of this pilot. Inespasa has developed, together with CATEC, a precise robotic drilling system in the framework of EVITA project. Okay. They find out in this during this project that also a manual drilling system has space in this sector with some requirements of the aerospace industry, but also mainly it has to be compact and lightweight. Okay, when I say compact, I mean that there's no space inside beside the motors and the electronic. And lightweight, we have to choose. They have to choose lightweight material for the case as aluminum. Okay, so that solution brings also some problems regarding the heat dissipation inside of that system, because the temperature produced by the motors also produce high temperatures in the surface, so it has to be touched by the operator. It can burn. It reaches like 60, 65 degrees, maybe 70 degrees in operation. Okay, and also if you use high revolution per minute, the motor can stop. Okay, so that was the problem to solve. And in our case, we proposed to Inespasa to use additive manufacturing, metal additive manufacturing with internal cavities and maybe some lattice structure like fins to dissipate that heat, okay, to improve the performance. So some objective of this pilot, of course, we have to manufacture the case to increase the thermal performance by adding active and passive heat dissipation. We have to compare, also the conventional case, the conventional solution with the additive manufacturing one. We need to decrease also the tooling. They want also to decrease the tooling for machining by proposing new post-processing, not only machining, okay? And also, and of course, seeking to optimize the technology already in place, okay? So these are the 4 main partners involved in this pilot, okay? The UPV, the University of Basque Country, has been in charge of the thermal simulation in coupons and in the final case. Really important when you are redesigning and having a lot of solution and options to have that information before manufacturing. SEIT and ENIT for the material characterization. As we were thinking about 2 alloys, 2 aluminum alloys, aluminum silicon tech magnesium and scalm alloy. It was also really important to analyze the density, the influence of porosity, microstructure, and its influence in the electrical and thermal conductivity of the material, okay? And from CATEC, we have been working on the redesign, the manufacturing, post-processing, heat treatments, and testing, okay? So, there's a lot of work in this slide, but I have to be a little bit quick because we have to talk about 5 pilots. But thanks to ENIT and SEIT, we have studied both materials, aluminum, both alloys, aluminum silicon and scalm alloy, about its influence in regarding the porosity or the densification, microstructure, heat treatments, and its influence in the electrical and thermal conductivity. As I said before, there's a lot of work, but as a conclusion of this activity, we can see that aluminum silicon has higher, not performance, but higher conductivity in terms of electrical conductivity and thermal conductivity, which means in the chart on the right that if we use scalm alloy in the case, the heat produced by the motors would have more difficulties to reach the surface and, for instance, burn the operator, okay? So once the material is chosen, we have manufactured some coupons to validate, let's say, or design or proposal. You can see there a gyroid, works like fins, okay? And what we call reticular structure that have internal cavities, let's say, so we can induce air inside that coupon, okay? We perform some testing. We heat and also we manufacture a solid sample, so we can compare with a nominal, let's say, material. We test these 3 samples by heating them till 85 degrees, and with infrared thermography camera, we monitor the warm-up and the cool-down process, okay? That's are the continuous lines, okay? And in parallel, the UPV make the thermal simulation of this testing to correlate the results, but also to feed this kind of software, because scalm alloy is not a common material in the database, so it's great to have also the slight difference to be implemented in the software also, okay? So as you can see, comparing the orange with the yellow, gyroid structure reach 85 degrees faster, but in the cool down process, they reach 28 degrees at the same time than reticular, which means that have the capacity to absorb that heat, but then difficulties to leave that heat, okay? And then if you see the green one, once that we put air on it, during the cool down, we don't put air during the warm-up to have the same condition. We reduce, if you compare the yellow one with the green one, we reduce the cool down process 2 times, okay? And if we compare the green one with the red one, we can see that we reach 85 degrees faster, but the cool down is decreased for 6 times, something like that, okay? So as main conclusion in here, the reticular, the internal cavities sample is a better approach than gyroid. And the other conclusion is that if we reach high temperature very fast with the reticular, so we have to make something else to avoid the motors to reach that temperature, not to avoid the stop. Okay, so our solution was to, apart of put that cavities, let's say, or channels, we put some holes to use the same air to blow the motors during operation, okay, to dissipate the heat, okay. So this is a roadmap of the design. You can see some image of the manufacturing process. We use laser powder bed fusion, heat treatment, okay, of the cases. We manufacture 3 cases. You will see later on 2 of them. One is a demonstrator, just let's say to show the internal cavities and so on, and 2 of them are functional. One of them we go to the interface machining with MEUPE to obtain that requirements, that dimensional requirements that they are higher in the interfaces. But also we implemented in this process a wire cut process as we have to extract the component from the building plate. We use the same process to make the interfaces of the other side, okay? And then the drilling and the threads manually, okay? Just to compare to post-processing. That is easier to have it in-house, okay? More than a 5-axis machine. And at the end, we use computer tomography to see the internal channels. So it's the only technique that gives you that chance to see inside and make that comparison between nominal and the manufacturing part. Okay? And then the final testing, we wanted to compare both solutions. We test in the same range. We put working through 300 revolutions per minute during 15 minutes. And we use, again, thermocouples and infrared thermography camera to monitor the heat propagation of both solutions. Okay. The results, there are some infrared thermography images. You can see on the top left that the conventional case reached 55 degrees in 50 minutes. Okay, it reached a thermal equilibrium in all the system. In the bottom left, the new design without air reached 15 degrees less. Okay, in the same time, and 48 degrees in the operator contact area. Okay. If we use the case like this, we can refrigerate then, okay? That is the right bottom, okay? So in less than 10 minutes, we could reach 25 degrees just with air, okay? But in the right top, you can see during 15 minutes working with air during operation, okay? And the maximum temperature that we reached was 24 degrees. So these results was really good for us. It was the expected also. So main conclusion, the final testing has showed really good results in terms of heat dissipation. In terms of warming up, if we reach difference of 15 degrees if we only compare a conventional with the new design. But if we put air, we reach a difference of 31 degrees, okay? And if we are working with that case without air, in less than 10 minutes could be operative again, okay? After 15 minutes working. Also, in terms of material characterization, by using scalum alloy, we have achieved better results because of its thermal conductivity, the thermal conductivity that has the material, okay? So. Also, we have redesigned the redesign of the case have achieved a 37% weight reduction. Sorry, and finally, we are still working on the last simulation process to validate the thermal simulation, and also in comparing the cost and the timing. We don't expect to be really competitive in terms of cost, maybe in time, because this is a really cheap. It's cheap to do it. It's aluminium and machining from a block is really fast and cheap. We are talking more about the functionality of the case. Okay. Either ways, if you have your entire process in your own facilities, for example, if you have wire cut and the drilling process is manually, it's really easy. It would be really fast if you produce, for example, in a batch for cases. And if you use high laser or manufacturing ratio, for example, we have manufactured with 30 microns, but you can use also, for example, 60 microns. So in time could be closer, okay? So that are the main activities that I can show in 10 to 12 minutes. Of course, I'm open to any question or during the coffee break or whatever you want.
Thank you, Carlos. Perfect. No, it's perfect. Do you have any question? Okay. Thank you, Carlos. So here I'm back again. I promise this is the last time. Okay. I will present the SOMOCAP pilot. Okay. During the project, we work with the SOMOCAP company. SOMOCAP is an entity specialized on mold injection with polymer material. Okay, and they give us the opportunity to work on a tool for injection molding. Okay, with polyethylene. The original part is this one. This is a core of an internal mold. When we inject polymers, so polyethylene, we have the core internal to create some holes in the polymer part. Okay. This part is originally machined from a bulky block of 40 CMD8. Okay, C45 still. The original part have a simply hole regulation, so it's a drilling hole, okay, with a back and with a go and back of the water. Final tolerance, okay, 0.02 millimeter with polish, 2 weeks of delivery time, and the original price is more than 5,000 euros because you have electro-erosion on the top and it's expensive. And it's performed internally by SOMOCAP industry. Originally, this part from a bulky block have a simple hole, so no real good optimization of the cooling. And when we are cooling the polymer part, when we remove the core of the mold, the hole is not cylindrical, but a little bit ovoid, okay? Because the cooling was not controlled and not efficient. Objective is to manufacture this part with additive manufacturing technology. Is a classical part we can manufacture with LPBF, okay? So powder bed fusion is classical technology we can use and the best use. But in Additool, we want to explore a new technology that is arriving on the market. This is the FDM metal charge. Okay, so we have made a webinar on it. I invite you to see it on Additool. The objective is to compare the conventional machine, like with a Marforge, and open system. So with two filament fabrication technologies, sinter, with and without HIP, orthostatic pressing. Also, we have to improve to increase the performance of this tool by adding conformal cooling channel inside, and if possible, reduce delivery time and the price, if possible. And just keep in mind that the part is about 200 millimeter of high. Okay, that could be a limitation for this technology. In terms of involved partner, so there is Estia, there is also the SEIT, Fadakatech, UP, Lortec, and Enit. So a big consortium to explore this new technology. Okay. And you will see we have a lot of work to improve it. The method we have used is first to characterize the material, a new material on the market. So we have chosen the H13 and the 17.4 pH, okay, for the hardness and for the longevity, the tooling steel, and for the 74 pH is stainless steel. So characterize the material and also the part manufactured just after. In the consortium, we can rely on two kinds of polymer machine, polymer and metal machine. The first one is the Marforge Metallics by Lortec, a closed system, but that works for this kind of technology. And then we have in Estia a Lancaster S600D and all the accessories. Accessories, it's oven for debind and oven for sinter the material after printing. Then we have to perform heat treatment, so debind and sintering with optimization of the value chain. Perform some tomography on the part to characterize the material, if there is some porosity, some cracking, bubbles, etc. Machine and test directly on the production lines of Somocap. This kind of technologies, the objective is to obtain an all metal part using conventional 3D printing technologies that you can have at your home. Metal additive manufacturing, if we take a look on the existing technologies, PBF, DUD powder, DUD laser, DUD wire arc, it's more than 500,000 euros, 1 million euros to give access to the technology. Okay, it's very expensive. With this, we expect to give access to SMEs and little entities to have access to metal additive manufacturing parts. So, make accessible this part with this technology based on metal injection molding process, the MIM. It's MIM-like. And then, if we can, reduce delivery time and the time to market. The raw material with this is a polymer filament, the feedstock. Okay? But this polymer filament is loaded with a metallic powder, and we have approx 18 microns D90 inside the polymer. So we print the part, then we have to debind it, so we have to extract quasi totally the polymer, So we call it, when we have at the end of the debinding process, the brown part. And then we have to sinter at just below the fusion temperature of the metal to obtain a solid and full part. This is a sinter part. Okay. Just note that you have a reduction on the scale. Okay. After the sintering process and after the debinding also, you have to manufacture a bigger part that at the end you have your tolerance. It's about between 19 and 26% approx. Just to give you some information, you have some providers on the market. You have BASF, a patent technology, okay, that are performing some stainless steel with a catalytic debinding, so with nitrogen, etc. That could be dangerous for a laboratory or for companies. Okay, so you have to subcontract to BASF the debinding. You have NanoE and Nanovia that are performing wires, filament with thermal debinding, so only an oven, one oven to do both debinding and sintering. And then you have Marforged with all the value chain. When you buy the machine, you have the washer with Opteon gas, and then you have the sintering oven. In terms of method, first we have begun with the parameter research to print with conventional machines this kind of filament. So we have made a lot of samples with cooling channels, with traction samples, cylindrical, etc. To be familiar with this technology and with this filament. Then, this is the main critical aspect. This is the debinding and the sintering. Okay, the printing is quite easy, but to debind and sinter is difficult. To debind and sinter well and to have good properties directly on the material. And we have to control it. For example, the first curve from the supplier, from the provider, is about 91 hours for debinding and sintering a part. So you have to launch the part on Monday, and you can give out the oven on the next Friday. Okay? So it's not industrial, 91 hours. So thanks to SEIT, they have performed a very good time reduction on the debinding and sintering, and we have less than 20 hours approx to debind and sinter. So you can launch a piece on Monday, and on the Tuesday you have it. So they have optimized all the value chain, performing some heap, orthostatic pressing, etc. on it. Then we print a lot of samples, as I said, and we take a look and we compare with the Marforged, with the conventional one, okay, where everything is closed. That's to say that we cannot change any parameter. Okay, you have the material, you have your geometry, at the end you have the part, but you cannot modify anything. But it works. It works, and before heap, we have approx 95% of density, and after heap, 98% of density. Okay, and you can see the geometry has not moved. You are not crackles, you are not bubbles, not deformed, contrary to a classical filament on the market, where before heap we have just between 81 and 86% of density. Okay, with the heap, we can close remaining porosity, and we have until 98% after heap. In terms of structure and analysis, ENIT performed a lot of analysis on it. This is just an example. For the H13, for example, you have a powder surface ratio about 46% on the powder, circularity about 0.8, etc., etc. and about 5% porosity and 5% porosity for the 74 pH. Lot of tests also for dilatometry to compare with the bibliography if we have an H13 and a 74 pH after the sintering, etc. In terms of hardness, we are very below the expected results. For example, in Marforge, for the H13, they announced more than about 400 hardness Vickers, and we have half of the properties. Okay, with 74 pH is okay. We are more close than the announced results. However, after HIP, for example, on a H13 you have on a RP002 traction 263 MPa, megapascal, and after HIP we can, with heat treatment, we can improve until 1,400 MPa. So you have very good results after HIP. Okay, so a heat treatment can improve the hardness, the traction, all the metallurgical aspect of the material. Then we have redesigned the part. So we replace a simple hole of coding channel by a spiral, by an helix with a go and back. Okay, so it's double helix inside to be as near as possible as the shape of the polymer. Okay, and with this we increase by 2 or by 3 the property of the coding system directly on the part. Okay, to be more closed with the polymer. 2 mm over thicknesses, because with this kind of technology we have to machine after and to be polished. Okay, and then we manufacture. The manufacturing is very tricky. It's very tricky because the part is around 200 millimeters. Okay, 170. But when you have to manufacture with a scale, so more than 220. Okay, with 20% of scaling. So you have to manufacture mainly on horizontal way. But the limitation is not on the manufacturing part, is for the oven. This is the critical dimensional problem we had. All the sintering oven we can have access is about 100 millimeter of diameter of cylinder. Okay, so it's necessary to put it horizontally, and this implies a lot of things. Just some words according the Rapidia technology. During the project, we discover a new technology. It's not a filament, but it's an aqua past. It's aqua gel, a past where the load of material is very high. In a filament, you cannot exceed more than 50% of powder. With an aqua past, you can increase to 90%. Okay, so you have less polymer, you have less material to remove on the debinding, you have less deformation, and it's an aqua technology, so you don't have vaporization, smokes on the oven. So it's very interesting. It's Canadian, and they accept to manufacture for us a part that is actually on test directly on SumoCap. I don't have yet the result to present you. You will have at the end of February. But this is something very interesting. Okay. In terms of conclusion, according to this pilot, the binding and sintering process have been optimized, okay, for the NanoE H13 filament, obtaining good external geometry and control carbon level. A final hot isostatic pressing can close most of the porosities, but it is necessary to have a first chemical debinding to open some pores to facilitate the thermal debinding, the next thermal debinding. Okay, and it works great for part with little dimension. When we have big part, massive part, you will have a little bit some deformation and some cracks that can appear. Okay, so for a little part of thin plate, it works. Bigger, it's more complicated. And it's necessary also to master perfectly the value chain if you have an open system. It's not because you have a classical machine that you will be able to manufacture this kind of part. Okay, you have to master exactly the debinding and the sintering. Something interesting that there is a new brand on the market that are expert on it, and there is new collaboration that is coming to create all the value chain. Okay, one printer, the second debind, the third one will sinter. The full manufacturing chain of commercial brand Marforge is already optimized, and there is good results on it. It's almost dense already after sintering, and with zip we close the remaining porosities. But dimensional restrictions exist in the Marforge also because you are married with the oven and with the sinter oven. Something interesting. This kind of technology can work in idle time. Okay, you can produce your part and go to the office, go back, etc. Okay, so this is very interesting. So don't hesitate to have a look on it. Yet at this moment, the technology was not ready for everyone, but we think that in several months, this technology could be more reliable. Okay. Yeah, nowadays, today, mechanical properties are a little bit lower than those announced, so be careful about it. Just to finish, just an information according the cost yet for the filament. So we have tested the NanoE Zetamix H13, about €500 per kilo. It's still expensive, okay, but like polymer filament before, you will have a reduction cost once the months will happen. Okay, and Marforge, the closed system, is about €2,000 per kilo, and it's okay for me. If you have any question, yeah.
Thank you for your presentation, first of all. Very
You're welcome.
Nice. My question is not regarding the FFM process, it's regarding the comparison with LPBF.
Yeah.
Because this part is quite high, obviously, but you can fill up the build plate with a lot of packing density.
Yeah.
So my question is around the cost and the production. If this is a production insert in the injection molding, how is the comparison between the FFF processes against a multi-laser machine of LPBF? Okay.
This part is not produced in serial. Okay, it is only one part. It's one mold. No, it's not a demonstrator. It's a real part, but for one client. Okay, the SOMOCAP manufacture some molds for customers. Okay, some customers, and they have to manufacture one part like this. Is only one. Okay. As I said before, the best technology to do this is LPBF. Okay. Because with conventional technology, you are not able to manufacture coding channel inside with helix, etc. We know about it, but it is a part. This part gives the opportunity for us to test the new technology. So in terms of cost, we are more expensive. Okay, not on the printing. On the printing, 1 kilo of manufacturing is about €500. The machine doesn't cost anything. 500. You have the debinding and the sintering process that cost a lot. For example, originally, with the NanoE curve with 91 hours, we consume one cylinder gas about 50 liters with argon and hydrogen. Okay, you have 91 hours of resistance on the oven. Okay, it's a resistive circuit, so you have a lot of electrical loss. So yet, no, it's not interesting. Okay. With LPBF, maybe if you have a lot of parts, yeah, you can fill all your plate with 10 or 12 parts inside, and there is very interesting.
Thank you very much.
You're welcome. Yeah.
Hi. The question is, considering that the sintering process is a quite problematic process to control because it's a thermodynamic, etc., and considering that there are some strange shape situations, are you thinking about to simulate it, to do something predictable, how to design and prepare the sintering process to have the results aligned, considering these problems?
Exactly. And it depends mainly according to the geometry, first of all, but also you have a great impact of the strategy of deposition. For example, on the 3D printer, you can have infill, perimeter, you can have a rectilinear, gyroid, etc. A lot of patterns, and depending the strategy you will use, you will have different results to do this. At this moment, we are not able to simulate this kind of deformation with, during the oven. This is something important we have to perform. But you have some design rules to respect. Okay, I explain all the design rules on the webinar, so don't hesitate to show it. And the design rules are they will be different between the Marforge technology and an open classical system. Okay, for example, on the debinding with the Marforge, you have two kinds of polymer inside the filament. You have the powder, you have polymer, and you have also second polymer. I don't say in English. La cire. Quarks. Okay. Thank you very much. With Opteon, okay, the first chemical debinding, you will open some pores, some channels inside the part to facilitate the extraction, okay? And this avoid to have a twist of the part or a deformation of the part. With the classical filament on the market, you have only one polymer, and it's more difficult to open some pores. That's why chemical debinding have to be performed before, with alcohol isopropanol, for example, etc. Yeah. So it improves a lot the debinding and the sintering process. But yes, you will have some deformation on massive part. I hope I answer your question. Yeah. Yeah, Arthur.
Okay. Thank you, Pierre, for your great presentation.
You're welcome. Thanks.
About the process, you told that this is a cheap process.
Yeah.
But really, tell us about the oven. Tell us about the heap. We need it.
We thought it was a cheap process. We thought it was a cheap process until we done the job. Yes, the filament, the wire feed, is expensive compared to a classical polymer. Okay, 500 euros is more expensive than powder for PBF, and expensive than a DUD process. The oven, the binding on sintering oven, is about 100,000 euros. About approx. You confirm? Say it. Yeah, a bit more, maybe, a bit more. Exactly. But with this kind of technology, you can manufacture your part and then subcontract. With BASF, for example, it's only 60 euros to subcontract the debinding and the sintering. You manufacture your part, you send to BASF. The week after, they send you the part again. Okay? But the debinding and sintering process is very expensive. Yeah, and it's a job. I have to to pass. Excuse me, Naya, for the time. I give the talk to Lexury. about the pilot of LAWAC. Next series is up to you.
Thank you, Pierre, for the introduction. So, good morning to everyone. I'll be in charge of presenting the pilot proposed by a French company, LAWAC. So, as you can see there, they are two different parts, but the geometry, the challenge in geometry terms is very similar. Actually, the complexity is very low. So, the main challenge comes here because of the tight tolerances that are accepted. And the use of these kind of parts are tools for control of other parts that are located in the top of these parts. So that's why the tolerances are very restricted. Normally, these parts are machined from a block, from a bulky block. And you can see there the price for each part. Mainly, the difference in the parts are the dimensions. Okay? And the material used is a high-strength steel. So, the main objectives to follow in this project have been to reduce the delivery time, to reduce or keep the cost, and to guarantee the performance or increase if possible. Well, you can see there all the participants that we were involved in this, in the development of this pilot. So the methodology followed started with a selection of material because the original material is not weldable. So we changed or we substituted by another high-strength material and taking into account that the mechanical properties were similar. Well, the material was the same for metallic powder and for wire. And after the selection, a characterization was done to accept it for the manufacturing. 3 different technologies were used, choosing the best strategies to obtain different benefits. For example, we used the DED wire laser to apply for the smaller part, the DED powder laser for the bigger part. In this case, the material was applied in the top of a base done by machining and with a cheaper material. And finally, the DED wire arc for the full big part, applying a previous redesign. Then the best manufacturing strategies were selected using simulation tools. And after the manufacturing of each part, dimensional control was applied. Then the machining was done to remove or to have smoother surfaces. And finally, the test. Test has not been finished yet, so it will be available, those results, along this month. So for the first technology, the wire laser, I wanted to highlight one of the main advantages that apply to this pilot, which is the low heat affectation. As I said, the tolerances are very tight, so the possibility of distortions need to be minimized. In the case of the powder laser, the use of powder gives us the possibility of obtaining high detail. So the machining step at the final step of machining will be not as long as for the other surfaces. And finally, the wire arc is the one that can offer a very high deposition rate. I wanted also to highlight that all of these technologies can offer not only the possibility to manufacture, but also to repair parts, which can give to any part or extend their life. So the first result about the characterization of the raw material, well, about the powder, the metallic powder, it was characterized, and the most important points to assure were the high flowability of this material, which is linked with the sphericity of the particles. We have to assure that these particles don't have any internal porosity, that the chemical composition is homogeneous, and that we have a Gaussian particle size distribution. Regarding wire, this is, well, the less specific tests are required compared with powder. So now I want to show you briefly the goals obtained in each step, okay, along the development of the pilot. Firstly, we made a parameter research in order to obtain with its technology sound weld bits and a proper geometry to grow parts. Then, with those parameters, we studied the strategies in each layer, between layers, and also in intersections. And once having all this data, we manufacture simple walls. From these walls, tensile tests were extracted in different orientations, in horizontal and vertical, to check if any anisotropy is on the part. Then we obtained the results of tensile tests in the different parts obtained with the different technologies. The results were very close to the reference. So, and well, there's no anisotropy. Regarding microstructure, we saw different microstructure depending on the zone. So we had heterogeneous microstructure, but looking also at the tensile results, hardness, which are again very similar to the reference material and quite homogeneous, and the fracture that was ductile, we conclude that this heterogeneity didn't affect to the overall properties. Regarding the part, for each technology and in each part, we applied an over thickness, taking into account the last part, the last step of machining. And concretely, in the wire arc, the technology, well, the part was also tried to redesign, taking into account to apply less as possible material in order to reduce the possible distortions. So we remove the bulky zones, we remove the base, and we add some slim stringers to avoid distortion during the manufacturing. We made some thermal and distortion simulations in order to optimize the interlayer dwell time during the manufacturing and having temperatures less than 150, which was a limit in order to avoid collapse or overhangs during the manufacturing. We located also the distortions in the parts, which were mainly located in the edges of the part. So it gave us a clue to take into account which zones of the part need to be have at cooler temperature to avoid, again, distortions, and the calculated distortions were about 1 millimeter. So taking all of previous work into account, we defined the robot path planning, and also the sequence of the robot in each layer, in order to have homogeneous temperature distribution. Then we manufacture the parts with the different technologies, with a robot and laser heads or welding torch. And we also apply monitoring, concretely thermal monitoring with thermocouples and thermal cameras. And well, I wanted also to highlight that in the case of the use of DED powder laser, the tilting of the part was also a challenge to overcome. Then once we obtained the parts, we applied scanning to make the best fit with the original design. And there we could see that the final distortion was around 3 millimeters. But we could compensate in the final step of machining that with the over-thickness applied at the beginning. We also saw the distortion due to the heat treatment, comparing before and after the heat treatment in the smaller part, and we saw that this distortion was negligible. So the data, or the most characteristic data for each part with the DED wire laser, you can see there the cost, the calculated cost. In brackets, you can see the cost due to the machining step, which is the main part. The printing time was around 2 hours, a little bit higher. And the main highlighting point in this case was that the printing time at the end is the third of the conventional machining of the part. In the case of the powder laser, you can see there also the cost, again being the main cost due to the machining step. The printing time was less than 2 hours, and with a deposition efficiency of the powder of 70%. The most highlighting point here is that we could use a lower cost material of the base, which is 62% less in price, and that we can obtain high level of detail. Finally, with the DED wire arc, the cost is the highest one for the bigger part, and again, being more or less the same percentage, the one that, well, the machining step, no? The printing time is 7 hours, but I wanted to highlight also in brackets the time of 2 hours and 20 minutes that belongs to interlayer dwell time. This is a time that can be optimized or minimized choosing other cooling strategies. We wanted to highlight here the high deposition rate and the material savings comparing with the conventional machining of a block. That was 40 kilos. So, as conclusions, 3 different technologies were applied to offer the best advantage for each part. The DED wire laser obtained a reduction of lead time of 66%. The DED powder laser offered a reduction of material cost using a hybrid or multi-material part. And the DED wire arc obtained a reduction in material waste of 63%. In this last technology, a redesign was needed in order to reduce the weight and hence the distortions, because we had to apply less heat input. Simulation demonstrated to be an efficient tool to select the most appropriate manufacturing strategies in terms of over thickness, dwell time, sequence of robot, etc. All the technologies obtained the part in hours from the cut to the near net safe part. A great reduction of material can be saved. This is more obvious for bigger parts. And also, these technologies, as I said, can offer can be applied for repairing, so they contribute to sustainability. The final machining step we saw in all the cases need to be optimized. So further training is needed in order to machine near-net safe parts and be more competitive. And finally, the mechanical properties obtained were very close to the reference, and no anisotropy was found. So, thank you. If you have any question, I'll be happy to answer it.
Yeah. Thank you very much for the presentation. Just one very short question. Was there a reason why you machined the sidewalls of the laser wire part? Or
It's not necessary to, of course, it's not necessary to machine the full walls, because we just want to have the contact faces with the part that is in control on the top of the part. But well, was something, a misunderstanding with the machining. Okay. Yes, but of course, it's not necessary.
And then your savings, was that then calculated with machining of the sides or
yes,
without?
With
so
machining.
You would save even more if you would just...
Yes, yes.
Mm-hmm.
Thank you.
Thanks a lot for the presentation.
Thanks.
Can you comment more about the aspect that the part made by a DEV wire arc is the one with the lowest cost? So you are comparing these different sizes of parts as well, right?
Yes. Yes. We didn't apply its technology for the same, because
the same part, yeah.
One part was smaller. The other part, what it was done, it was just to apply in the contact faces material, so it wasn't all the part manufactured, and a wire arc was applied to build the full part.
Okay, thank you.
Thank you.
Thank you very much for your presentation. Just a short question. Did you make any heat treatment, or you just used the material as printed?
The heat treatment was applied. It was a low temperature heat treatment, just to remove residual stress. In the case of smaller part, I think it was around 40 degrees, no, more or less. Yes.
40 degrees?
Yeah.
400, you mean?
400, sorry.
400.
Yes.
If you have another question, I propose to ask to Lexury at the coffee. We are a little bit delay, okay, a quarter. Thank you, Lexury, for your presentation. And to finish, the last two pilot, Portuguese one. So I welcome Fabio and then Arthur for the pilot. It's up to you.
So, good morning, everyone. My name is Fabio Simões. I'm a mechanical engineer. I work at CDRSP, which is a research unit of the Polytechnic of Leiria. And I'm here to present the pilot number 1 from Portugal. That's the wrong one, unless you want to start. So, as I was saying, I'm here to present the pilot number 1 from Portugal. This pilot is let's say, a classic case of an injection molding insert. It's a very small insert. Actually, I've brought it here with me. As you can see, it's quite small. Okay. This insert is a part of a pair of inserts which are inserted into a mold, which is a rotating mold with the bimaterial injection. So it's an elastomer with a thermoplastic as a base. So this insert will actually be used to form or to mold the thermoplastic part, and then the other part, the elastomeric part, is injected on top of that. So the objectives of the pilot are to manufacture this insert by using laser powder bed fusion, followed by finishing operations using milling and EDM. And these finishing operations are common to both the conventional existing inserts and this one, so they're the same. Obviously, the main output of this is to apply the conformal cooling channels inside this small insert. The original version of the insert had no cooling whatsoever. So in the mold, this has no cooling, apart from obviously the base cooling system of the mold itself. But this part has no cooling. Also because it's a sliding movement, so it will slide in and out to form the part, so it's a bit difficult. But we decided to use this part anyway as an example, and we were able to build a conformal cooling channel inside and then compare it with the non-cooled version and a possible conventional cooling system that we could also implement. The main output of this will be a economic viability study to see how many parts we can build until we gain the value that we pay extra for the insert. So this is the mold. We can see the insert here, and there's another insert there, because the mold, as I said, is a rotating mold. So this is a bimaterial mold. And the first step is the thermoplastic injection step. Then the mold rotates, and then the second material is injected on top of that. So in each step, we have two materials being injected, or one material by each time. And then we have two inserts. So the big opportunity here is we can compare the performance of both the conventional solution and the conformal cooling solution on the same mold. So this one will be the conformal cooling channel, cooling insert, and this one will be the conventional without any sort of cooling. Okay. So the partners involved on this pilot were us as the ones who manufactured the insert by laser powder bed fusion. Also, we did the thermal simulations about the cooling, and SEED and ENIT performed the powder and the material studies regarding the performance of the material, the mechanical properties, etc. So the first task was to redesign the existing inserts, adding these internal cooling channels which weren't there in the first place. This is actually not the final geometry of the insert because these channels were switched, they were optimized. They are now more like following this contour of the molding area. Following this, we performed thermal simulations of the cooling of the plastic inside the mold to understand the differences. We'll see that in a minute. And then we the partners performed the powder and the material characterization to understand the properties of the parts. We then went to the production of the insert by SLM, the finishing and milling by milling and EDM at our partner company Mold Tipo. I forgot to mention, they're the ones who provided the mold. It's an existing mold. And after that, we performed a few injection tests, and they were performed simultaneously for conventional insert and conformal cooling insert. And then we performed an economical study. Also, we will be performing dimensional analysis of the injected parts. So the thermal simulation yielded these results. So these are the models for thermal simulations. The first model is the existing no cooling material. Then we decided to put the hypothesis of creating an internal conventional cooling system, which is very simple, could be drilled, okay? And then we use the third one, which is the conformal cooling, which was a bit closer to the molding edges. As I said, this is now a bit different. It's more like this, okay? It's a little bit optimized, but nevertheless, we will see it's not much different from possible conventional cooling which could be implemented. This is the thermal simulations results. So what was done here is we considered 2 cooling times, and in those cooling times we studied the state of the melt. So if you see a blue area, it means the plastic is still liquid, so it's not solid. Anything that is white means the plastic has frozen already, so it's cool. After 8 seconds, we can see that without any cooling, we can see the blue areas here still with melted plastic. With conventional cooling, that is, if we were to use conventional drill channels, we will have a significant reduction of these non-melted, still melted zones, and conformal cooling also even better, okay? A little bit better, but somewhat better. So if we, in terms of thermal simulations, if we compare the cooling times, we can see that without any cooling, we have approximately 15.74 seconds in terms of simulation, whereas for conformal cooling, 10.27, 10.34, which means even if we were to place conventional cooling channels on the insert, we would get very good result. But actually, they are not there, okay? So this is 35% cooling time reduction. Then these are the results for the powder characterization. We use this commercial powder from Bowler, W360. It's a tool steel, okay? It's a very hard tool steel. Our partners at SEED, especially at ENIT, had some trouble with testing the material for their very high resistance and mechanical strength and hardness. The powder, everything is more or less okay with the powder in terms of sphericity, and for laser powder bed fusion, no problem. And the microstructure and then the specimen characterization were performed by ENIT. We can see a very good density, typical microstructure from the SLM without any sort of heat treatment. We can see that here as well. So this is also this also is inspiring us, especially ENIT, to proceed with further studies, especially for heat treatments of this material, because the results for this kind of structure are different than from the results of our wrought steel. And ENIT also noticed that the outer layer was a different, presented different microstructure from the rest of the bulk material, and we also have some micro cracks there, which were apparently not very problematic. Okay. In terms of mechanical properties, we have a very high hardness, very good as no heat treatment resilience, high ultimate tensile strength and low ductility. It's a tool steel. And some anisotropy depending on the building direction. So we send them a very high amount of specimens, and they perform these mechanical tests. As I said, in the future we'll be conducting high temperature tensile tests to perform the study of heat treatments. And so after this, we manufacture the insert. This is the insert manufactured in both sides as it came out of the platform on our SLM machine. After that, it was machined at the partner company, Molde by milling and by EDM. And then it was assembled in the mold. As you can see, this is the mold, and this is the rotating plate that contains all the inserts and the rest of the assembly. As a further detail here, we can see the insert is there. And we can see the hoses that will convey the water for inside the insert. So this is a sliding mechanism. And you can see there's a secondary, or a second one, which is a conventional one without any sort of cooling. Okay. So then the mold rotates and you get an injection per cycle. So the injection was made with the material, POM. This was sort of on purpose to try to make a difficult material, because POM will get a lot of contraction. So the idea was to ascertain the level of contraction of the parts after the injection molding. So we injected these parts. These ones are from the conformal cooling channels, this one. and these ones are from the other one, conventional one. There are slight differences, there's some defects, but this is not about the cooling itself, it's just about the finishing, differences in finishing of both the inserts. We tested with 2 cooling times. So 16 seconds, it was like the baseline definition for no cooling. It was on the machine, the operator this was like a previous setup. Then I asked the operator to, well, let's try and reduce this to 10 to see what happens. 10 seconds, you will get parts anyway, with both the inserts, okay? So it doesn't matter. But after some time, the machine starts to give you some problems about with the injection, with the cleaning, parts start not coming out, ejecting properly. So there's some difficulties there. But now it remains to be seen how these 2 parts compare in terms of distortions, warpage. So that's our next step, and it's still ongoing, okay? Before that, we were able to do a very simple economic study just to understand what the impact of the solution was, and considering that the conventional insert would cost something like 2,500 euros, and this additive manufacturing insert would cost practically double, then we would have these common operations, okay, which will be valid both for the conventional insert, which is already included here, but we have to be added to this 5,000 euros for the additive manufacturing insert. Those operations by finishing an EDM, considering the hourly machining cost, okay, so the injection machine, the installations, whatever, the company told us something like 40 euros per hour. And considering that the cooling time cycle could be about 6 seconds per part, okay, we came to the conclusion that for 45,000 parts, we'll have the payback of the initial cost difference, okay? So 45,000 parts is a very small number of parts. So obviously there are 2 perspectives on this. Either you see this as a number of parts, so a payback time, or you can see it, if you have a fixed batch size, you have a savings in time, obviously savings in energy in the end, okay? So both things. Anyway, it appears to be economically viable to use AM technologies to produce this part in particular. Nevertheless, since it is a very small insert, the advantages are not as clear as in some other cases where you have bigger inserts, bigger parts, bigger savings, okay? Although you have obviously a bigger initial cost. So it's a very small insert. We can see here there are 4 holes, so 2 of them are for fixation, and 2 of them are for the cooling channels. They are inside, but the part itself being so small, if we were able to drill these conventional holes in the side, the difference will not be, probably not that great, okay? But that remains to be seen. Anyway, comparing with the initial solution, it is obviously better and feasible, I think, to use this method, okay? Okay, thank you. Any questions?
Thank you. Thank you for the presentation. Amazing work. The conformal cooling is really interesting strategy, but did you do any sensitivity to the material thermal conductivity? Because the tool steel is very hard, so on, but the bullers, this commercial of bullers has very low conductivity. So did you explore?
No,
just numerically, I mean.
No, we didn't explore the numerical part or the thermal conductivity of the material itself. We consider the baseline thermal conductivity but not any variation of that parameter. It could be important because it's a very small insert, so it could be very relevant to use that.
Okay.
Yeah, it's a good suggestion.
Hello, thank you again. I saw that the cost of 5,000 euros for this part seems quite high. What was the assumptions behind? I did some consultations with local suppliers of this kind of service. It's probably not the cost for a company internally. It's a cost of something if you want to buy this from someone for a supplier with the manufacturing.
Okay, so the price to purchase.
Yeah.
From a SUDOE.
Okay, so it's probably smaller if you have this in-house or something. Okay.
Okay, thank you.
Okay.
Okay, thank you very much.
Thank you.
Fabio, for your presentation. Now, up to Arthur from Ipeleria also to present the last pilot of Additool. And then, after presentation, we will have a coffee break, maybe. It's up to you. I give you the talk.
Okay, good morning. Bom dia. Buenos dias. Bonjour. And here in País Vasco. Oh, okay. Okay. Okay, I came from Marinha Grande, from the Center for Rapid Sustainable Product Development. And I don't know. I came to talk about the second pilot in Marinha Grande regarding the glass tooling sector. In Marinha Grande, I don't know if you know, but we have there perhaps the square kilometer where more glass is produced per hour. Also, we have there a big Spanish company, Vidrala, and also we have will play an important role in the tooling sector of plastics, but also in the tooling sector of mold making for glass industry. Okay, the presentation of the component, you know it. So it's more packaging for the glass industry. This is a schematic way to present all the process, or a part of the process. This is the ES section machines where the plastic is blown, and then we have a change on direction to put all the bottles inside a annealing chamber. This is the aspect of the ES machine, of the individual sections. The machines have a high rate of production. More or less the cycle is 5 seconds per bottle, in 2 stages, starting stage and second stage. Also, I have here. Okay, the production rate is too high. Is too high, and we have a lot of sections with a lot of similar molds. So means that each mold needs to get from each mold. You need to get a lot of production, and also we need to have a lot of molds, and that means that perhaps the molds are very cheap. Needs to be very cheap. This is the aspect of the annealing chamber, the outcome of the annealing chamber. Okay, we look to a mold like this because we have those straight lines bottles, but the more difficult are these kind of bottles that this is a bottle, a small bottle of 0.33 centimeters cubic of liquid. So the bottle is quite small. It's 138 diameter and 174 millimeters tall. This is the schematic of the 2 stages. Here we have the starting mold, and we have a rotating for the blowing phase of the bottle. In this stage, we need more or less 2 minutes. 2 seconds, and in this stage we have more or less 3 seconds. So it's very quick. I don't know if you know, but one of the costs, biggest costs in this kind of industry is compressed air. Now is gas, but perhaps 4 years ago it was compressed air and then gas, because each mold needs to be cooled by air. Okay, and these kind of companies are not used to use conformal cooling because molds are really very not expensive. So this is the hand tooling for the blow molding of the glass, and then they use usually the vertiflow. There's a vertical flow on the tool from the bottom to the upside. And this is every 5 seconds we have this cooling stage. What we did, it was go from a vertiflow approach to a conformal flow approach, as is used to do in injection molding. Also, we think to go a little bit further, to have a lattice sector, to reduce the mass, perhaps not thinking about the cost, but thinking about the inertia of the cooling, and have also the position of DAD of an Inconel steel. Because we need to have here two conditions. One is tenacity, and another one is resistance to heat at high temperature. So we need to have, here we use the stainless steel produced by SLM, and then we cover it with our colleagues from UPV with DAD and Inconel. This is the aspect of the conventional tool with vertiflow and conformal cooling. We made some preliminary tests by making some simulations, and okay, it's clear that we achieve a bigger homogeneity when we have a conformal cooling. Usually, the temperatures that are in the process came from 1040 degrees in the melting state. Molding state is more or less in starting of the tool is 1000, and then in the blow phase we go to the 600 to 400 degrees. We need to perform some testing on geometries, and we look to a curved part of the bottle just to have some samples and several samples with different geometries, and we test it by using some acquisition from FLIR, and also imposing some heating in that sample, and also the cooling with the airflow. Okay, and we make a lot of tests. I could show that we start with this is a conventional. Then we also use the lattice and the circular. Also, we change the diameter to provide different velocities profiles. Also, we went to elliptical without and with some fins. Okay, to try to get and see the influence of the shape in the conformal in the cooling rate. These are only some tests, but we from the tests that we start into 200 degrees, 500 and 600 degrees, and we have a reduction of more or less, if you have a straight line, a vertical line, we could see that here the green is the vertiflow, and the others are the conformal with elliptical, with fins, without fins, but we achieve 10% of reduction on cooling time. This I think is for 600 degrees. The other one it was for 500. I don't show here the 200, and we look also to several surfaces because we have a molding surface on the other surfaces. Okay, by the end, we produce some tools by using a SLM EOS machine. 6 days, I think. It was only yesterday I saw that value, and I look and, oh, it's true. It came in an email, but it's 6.5 days. Then the coating, it was made in UPV, in a truth machine, and the big challenge it was to make it in the 5-axis continuously, and also I have here a video. I will try to go over it, okay? So, but this is a machine of UPV, Okay, this is the aspect. I think it was this week. Yeah, this week. So it's better to go. And this is not the final. We need now to make the milling. Okay, I could have here some more conclusions, but this company that we work with, Vidrimold, is one of the biggest players also in the world making molds for glass. They are now in the process to buy a DAD machine, thinking about not in SLM, but thinking about to cover the milling parts by another alloy to have air resistance. Already they are using ultrasonic deposition and also plasma deposition, but they are now going to DAD, and this sample will be good also to them to have sure what they are buying. Thinking about, let's see, thinking about in price, one tool for molding of, for blow molding of glass costs more or less 200 euros. If you think of these have 6 days of processing only in SLM machine, 5 kilos. Okay, it's not so expensive as 5 kilos, but we'll turn that we have more or less 4,000 euros of only on that. We didn't try it in the real conditions because it's quite difficult and quite impossible to stop one of those stations to put their testing sample. We could did this thing, but I imagine that could be interesting as the AM power told that the CO2 in this kind of process could be reduces a lot because we are working with a very energy consumption industry. Okay, so I think these are not. I didn't put this here, but the tool have a high cost. But I think what we could achieve is really in the process, the millions and millions of bottles and the reduction of energy consumption in air, gas, and by the end in the CO2. Okay, thank you very much.